Hey folks, in this video we're going to go through a calculation that I'm assigning you for the light module. And here's the basic idea. What we have is a laser beam that can be fired at the moon. And because laser beams are beams of light that don't spread out very much, it's what's called collimated. We talk about this. So a collimated laser beam, there's the term right there, collimated, just doesn't spread out very much. It does spread out some. Certainly if you've used a laser pointer, you know that it is different from a flashlight. Flashlight beams spread out quite a bit. So it does spread out some, but it doesn't spread out very much. So we can direct a laser beam at the moon's surface, and there are reflectors on the moon's surface, so you can see one here in this diagram. This was a reflector placed on the surface of the moon by the Apollo 11 astronauts in 1969. There are other reflectors present, and there are other ways to measure this, but we can shine that laser light at the moon at the reflector, and that reflector will reflect it back toward the Earth, and we can detect the reflected light coming back to the Earth, and based on that we can do a calculation of the distance between the Earth and the moon at that point in time. So here we've got a situation where what we're saying is we're firing a 200 picosecond, and that's actually a pulse of light. So the laser light is emitted in a pulse that lasts for 200 picoseconds. 1 picosecond is a trillionth of a second. So we have a situation where this is clearly a very short period of time. All right, that's 10 to the minus 12 seconds. So a very, very short pulse of light is fired at the moon. The other characteristic here is the energy of that pulse, and that energy of the pulse listed here is 150 millijoules. That's what MJ stands for, milli, right? And remember that stands for 1/1000th. So 1 millijoule is 10 to the minus 3 joules, okay? So we now have that. We have a 1 picosecond pulse of light with an energy of 150 millijoules and a wavelength of 532 nanometers. So here's our symbol for wavelength. Nanometer, and again, nano stands for a billionth. So that's what we've got. All right. Now the lasers. So laser actually is indicated here, and and I certainly encourage you to research or ask questions about lasers. I have lasers in my research lab. But basically, laser is an acronym that stands for light amplification by stimulated emission of radiation. That's a mouthful. And what the heck does that mean? Well, we're not going to go into it here, but I certainly am available to answer any questions you might have about lasers and how they function. So again, they generate collimated beams of light that don't spread out very much. A flashlight may, go something like this, spread out, and a laser beam may be something like that. Doesn't spread out very much. It does spread out, but it doesn't spread out nearly as quickly as a flashlight beam. The other important characteristic of laser beams is that they are highly monochromatic. And what that means is they are at a very narrow range of wavelengths. Again, a flashlight is emitting light over a broad range of wavelengths throughout the visible region of the spectrum. All right. And remember, we define visible as 400 to 700 nanometers in wavelength. So a flashlight emits throughout the visible region of the spectrum. A laser beam, however, only emits a very, very narrow range of wavelengths, and the range actually depends very much on the type of laser that's being used. But with a laser beam, we can actually specify, in this particular case, that it's emitting a wavelength of 532 nanometers, plus or minus a fraction of a nanometer is what that would be. And 532 nanometers clearly is smack dab in the middle of the visible region of spectrum. If we were to look at that beam, it would be green. Chances are pretty good, if you've seen a green laser pointer, that it's a 532 nanometer laser pointer. Not a guarantee, but a lot of them are. And that comes from a type of laser that is actually called a neodymium YAG laser. Just for additional information, it's not particularly important to this, but where it's a solid state, it's a crystal, is the material that's used for the laser, and this is an element, neodymium. It actually is an ion with a +3 charge, and it is doped, it's embedded in a crystal of yttrium aluminum garnet. And again, that sounds strange. Yttrium is also an element, aluminum. And garnet is a type of crystal that it's embedded in. So that's actually a fairly common laser. It emits, it's useful for a lot of applications. So the 532 nanometer light is being generated through a process from the emission of a neodymium YAG laser. That 532 nanometer wavelength light is shot at the reflector on the moon's surface as a pulse. The pulse is very short in duration. As we noted here, it's 200 picoseconds. All right. It has an energy of 150 millijoules and a wavelength of 532 nanometers. So what you're going to need to do in this particular problem is to calculate, first of all, the frequency of this 532 nanometer beam. 532 nanometers being the wavelength. And again, just to clarify that, I certainly encourage you to look at some of the other calculations, example calculations that I have posted for you. So that's the wavelength. So first calculate the frequency in the problem, then calculate the energy of a single photon in the problem, and then knowing that this 150 millijoule laser pulse actually consists of a lot of photons. So if you add up the photon, you add up the energies of all the photons, it adds up to this 150 millijoules. So then the question is, how many photons are present in that 150 millijoule pulse? So again, you know the energy of a single photon, which you will calculate. You know the total energy is 150 millijoules. How many photons are present? I'm not going to go into more detail there, so think about it and how you might do that calculation. And then, so what was the point of this exercise to begin with? And why are we aiming the laser at the moon? We're aiming at the laser at the moon to determine the distance to the moon. So what's critical is that we measure the time it takes for the laser pulse to go to the moon and back. All right, and in this particular case, it's indicated that we have a time of 2.56 seconds it takes for the laser pulse to get to the moon and back. So, can we calculate the distance to the moon? What information do we need to calculate the distance to the moon? This is actually the kind of question we asked early on in our discussions of motion. If I want to calculate the distance to an object, and I know the time it takes to reach that object, in this case to reach that object and back, How do I calculate the distance? What other piece of information do I need for that? So that's basically the objective of this calculation. I hope this helps to explain it. Certainly, as always, ask questions.